In today's video, we're going to learn about another type of function called logarithmic functions. In our previous video, we talked about exponential functions. And to get us started, to help us understand where logarithmic functions come from, I want to take a look at this example. So this exponential function I'm actually going to have represent money in a bank account. My principal amount, my starting value is 1,000, right? So 1,000 is how much I started with. And then in this case, since I'm multiplying by 1.05, I'm earning money, right? It's growth. But specifically, I'm earning 5%. Okay, I'm earning 5% interest. Where's the 1 coming from? Well, that's because if you're earning 5%, you're still keeping 100% of what you had before. And so you're multiplying by, after a year, you're going to have 105% of what you had previously. You're multiplying by 1.05 each time. So here's my exponential function. But what if I was wondering, how long is it going to take me before I have, I don't know, $5,000? Let's dream big. How long is it going to take before this value reaches 5,000? Well, what would that mean I would do? That means I would set this equation to equal to 5,000. Okay, well, I can divide both sides by 1,000, but what I end up with is 1.05 raised to the t equals 5. How do I solve something like this? I can't use any of my basic operations to get t by itself because t is up in the exponent. So how do I get it down from being in the exponent? Well, this is where I need logarithmic functions. So, what a logarithmic function is. Y is equal to log b of x. And what it does is it answers the question of what power would I need to raise my base to in order to get x. Okay? So for example, our example from above, what this would turn into is log base 1.05 of 5. Because once again, it answers that question, what would I need to raise 1.05 to in order to get 5? What power would I raise 1.05 to in order to get 5? So that's what a logarithmic function does. And the important thing about a logarithmic function is it's the inverse of an exponential. It's the inverse of an exponential function. Okay. What does that mean about b? Because b represented my base of my exponential function, b must always be greater than 0, with the exception of 1. Okay. Well, notice, if you were to graph a log function, what do you get? You get something like this. And hopefully you notice how this is, oh, actually, no. This is very similar to an exponential function, just flipped across y equals x, because a logarithmic function is an inverse to an exponential function. In fact, it has similar properties to exponential functions, just reversed. In this case, the domain is from 0 to infinity. Okay, those are the numbers you can plug in. It's what the range of an exponential function was. I can't plug in a negative number into a log function. You'll get an undefined value. I can't plug in 0 to a logarithmic function because there's no exponent you can raise a number to in order to get an output of 0. The range, though, you can have anything from negative infinity to positive infinity. An exponential function has an intercept, but instead of a y-intercept, it's an x-intercept. And it's at 1, 0. And the 1, 0 in this case, if you have some starting value before log bx, then of course it would be like a naught or something like that. Logarithmic functions also have an asymptote. But in this case, it's a vertical asymptote at x equals 0. My graph flattens out as it approaches the y-axis. Okay, so very interesting. So if I gave you an example and asked you this, what is log base 3 of 81? Of 81. What is this asking? It's asking, what power would I need to raise 3 to in order to get 81? Right? It's asking this very question. 3 to what power equals 81? In this case, that power is 4. 3 to the 4th power is equal to 81. Okay. What about this one? This one's a little bit more tricky. What is log base 4 of 1 over 16? Interesting. I put in a fraction. Is that allowed? Absolutely. It's in my domain, right? It's greater than 0. What power would I need to raise 4 to in order to get 16, or in order to get 1 over 16? Well, since my numbers are ending up in the denominator, it's probably going to be a negative value. And since 4 squared is 16, my answer here is negative 2. Okay. Next, let's talk about some properties of logarithms. So logarithms actually have some really important properties that make them really easy to work with. These properties are based off of the exponential properties, which makes sense because logarithms are just the inverses of exponents. So here are my logarithm properties. Property number 1, if you are taking the log of log base A of two values being multiplied by each other, okay? Lowercase a is just whatever your base is. These properties are true no matter what your base is. So it doesn't matter what your base is, these properties are always true. So if I have log base A of A times B, it turns out you can split that into two separate logarithms with addition. Okay. Similarly, if you have A divided by B, since division is the inverse of multiplication, you end up with log base A of A subtract log base E of B. Okay. Well, what happens if you have an exponent inside your logarithm property? Well, using my exponential properties, we actually see that you can pull that exponent out in front of your logarithm and just take the logarithm of whatever your base was of x. Okay. So these are three really important properties with logarithms that let me play around with them quite a bit. Okay. Beyond this, it's also important to recognize how these work as inverses. Take a look at this. What would happen if you took the log base b of b to the n? Or sorry, no, let's do x. Sorry, I want to do x. Well, what is this asking? This is asking what power would I raise b to in order to get b to the x? Well, the answer to that is precisely just x. If I switch this around and do b raised to the power of log base b to the x, what do I get? Well, what this is saying is log base b to the x represents, okay, what power would I raise b to in order to get x? And then I'm raising b to that power. So I end up with x. So do we see how these two functions cancel each other out? If I take the log base, if I take the log of b to the x with base b, those cancel out and I'm left with x. If I take log base b and I put it as a power to a base b, they cancel out and I'm left with x. Okay. And last but not least is a very important property that we'll talk about moving forward. If you have log base b, you can actually change what the base of your logarithm is fairly simply by doing log base a of x over log base a of b. So I can change my base to where I was working with log base b, but now I'm working with log base a. Okay, so why are these logarithm properties helpful? Well, the first reason is because logs require you to be talking about a specific base, I have an infinite number of log functions, right? Depending on what base I'm working with. That's true with exponents as well. But exponential functions are a little easier to plug into your calculator than log functions are. If you look at your calculator right now, there's not a button for log base a, or there's not a button, even if I go up to my beginning example, there is not a button for log base 1.05. And that's because these properties allow me to, instead of working with different bases all the time, to really just focus on to focus on logarithms that we commonly use. And in our case, there's two logarithms that we use more often than any other ones. So my common logarithms that I use more often than any other ones are log base 10 and log base e. Okay. Log base 10, of course, because we work with a base 10 system. So if you ever see log without a base specified, that's log base 10. But then log base e, that one's used a lot because e, like we said in 3.1, e has that special property where e to the x, the derivative of e to the x, is itself. And for that reason, we use e a lot. And so this is called the natural logarithm, which I've already mentioned before. It plays into my derivatives of when my base is not e. Okay, so this is called the natural logarithm. So to highlight the fact that we can just use my common logarithms instead of using logarithms with very specific bases, I want to return back to that problem we started with up at the top, right? We ended up with this 1.05t, or 1.05 raised to the t power is equal to 5, and we were unsure how to solve it. Well, like we said earlier, using just what a logarithm is, I could go ahead and just do log base 1.05 of 5 and see what that gets me. But once again, log base 1.05, that's not something we commonly use. That's not an easy thing to find on my calculator. So instead, let's use one of my common logarithms. And you're going to notice I prefer the natural log. So I'm going to use the natural log here. So what I'm going to do is I'm going to take the natural log of both sides of my equation. Okay, what does that leave me with? That leaves me with the natural log of 1.05 raised to the t is equal to the natural log of 5. Now I guarantee you the natural log is an easy button to find on your scientific calculator. So this natural log of 5 part over here, that's something I can just plug into my calculator nice and easy. I can plug in natural log of 5 and get out a value. Well, on the left side, I have the natural log of 1.05 raised to the t. And just to be clear, this whole thing is inside of my natural log. Well, knowing that, I can use logarithm property number 3. Since I have an exponent inside of my logarithm, I can pull that exponent out. And I'm left with t times the natural log of 1.05 equals the natural log of 5. And there we have it. I've done it. I was able to get the variable out of the exponent using my logarithm property. And now I can solve for t by dividing by the natural log of 1.05. And I'm left with this. What you'll notice is precisely the change of base formula, but just using the natural log, right? I'm using the change of base formula on log base 1.05 of 5. And that's going to give me how long it takes for my money to grow. So the next thing I want to show you guys just real quick is, now that we know what the natural log actually is, why does it show up, why does it show up in my derivative formula for a basic exponential function, for a to the x, right? I get natural log of a times a to the x. So why am I getting a natural log in there? Well, the reason why is because if I think about a to the x, the e function, e to the x, right? E to the x had a much simpler derivative. So it might be helpful to get my function in terms of e to the x. But in order to do that, I have to use some of these inverse properties here, right? So recall that e to the natural log of x is just equal to x. Okay? And more importantly, so what that means is e to the natural log of a is equal to a. Aha! So what I can do is I can replace this with e to the natural log of a, all raised to the x power. Well, according to my exponential properties, I can just multiply these two exponents. And so I get e to the natural log of a times x. Well, now, this right here is in the form e to the kx, right? Natural log of a is just a constant, so this is in the form e to the natural log of a, and so I can go ahead and take my derivative. dy over dx is equal to natural log of a times e to the natural log of a times x. Well, what is e to the natural log of a times x? It's just what y is, which is a to the x. And so I get natural log of a times a to the x. And that's where that derivative comes from. It's using some of these logarithm properties with the natural log. So now let's talk derivatives of log functions. Okay? Well, because e to the x has such a simple derivative, let's actually start with the natural log of x. What is the derivative of the natural log of x? Well, in order to show this derivative, I'm going to write it as a two-sided equation with y as my output. And I'm going to use implicit differentiation. But first, I'm going to use I'm going to raise both sides as powers of e. What does that do? On this side, I just have e to the y, but what is e to the ln of x? Well, we just talked about this. Those cancel out, and I'm just left with x, because those are inverse functions. Now, I can take the derivative of both sides, because the derivative of e to the y is just e to the y. But because I took the derivative in terms of x, I also need to multiply by dy over dx. Derivative of the right side is just 1. So now I solve for dy over dx, and I get dy over dx equals 1 over e to the y. But now I need to get this back in terms of x, right? What is y again? Y is natural log of x, but I can even look right here. E to the y is just x. And so I get dy over dx is just equal to 1 over x. So it turns out that your derivative of natural log is this really simple function, 1 over x. Okay. But what if it's not natural log? What if I just have log base b of x? How does that affect my derivative? Well, it affects in a very similar way as like when we were taking the derivative of a to the x. What I end up with is 1 over x, but I also have to multiply by the natural log of my base. This time, though, in the denominator. Okay. Very nice. So those are my derivatives of my logarithm functions. Let's try an example. So, let's look at f of x equals, natural log of x to the 9th over 9. Well, what is this derivative going to require? I have a function inside of a natural log function. So this is going to require chain rule. Okay, so chain rule, I take the derivative of my outside function, the derivative of natural log of x, or derivative of natural log of u is just 1 over whatever that variable is. So I get 1 over, but then I keep the inside function the same, x to the 9th over 9. And then I need to multiply by the derivative of the inside function, which is 9x to the 9th over 9. Oh, sorry, not to the 9th, 9x to the 8th. Right? Power rule, you decrease the function, or decrease the exponent by 1. Okay, and now I can simplify. This 9 and this 9 cancel. And if you have a fraction in the denominator, remember, you can just flip and multiply that. So I end up with 9 over x to the 9 times x to the 8th. So 9x to the 8th over x to the 9th. Some of these powers of x's are going to cancel, and I'm left with 9 over x. Very nice. Okay. Good luck with the homework on this one. Let me know if you have any questions.